Good day everyone, this is the module 2 of engineering economy. This is about the money-time relationships and equivalence. This includes the interest and the time value of money, the concept of equivalence, cash flows. So the duration of this module is 1 week. For the introduction, engineers deal with maintaining the profitability of all assets, including money. Thus, the time value of money is important for an engineer because the capital is being committed by an entity for extended periods of time, which implies that the effect of time on money is very crucial. So in this module, you will learn about how interest and the time value of money, okay, as well as the concept of equivalence and cash flows. For the objectives, after careful study of this module, you should be able to do the following. Solve the problems including simple and compound interest. 2. Understand the concept of equivalence. And last is solve the problems involving cash flows. The pretest, in a separate paper, you will just write anything you know about the topic. Okay? And you can add also your expectations about this module and rate your knowledge from 1 to 5. 5 is the highest about each lesson stated in the objectives. For the lesson proper, let's go to interest and time value of money. First is the definitions. First is capital, wealth in the form of money or property that can be used to produce more wealth. So that is the definition of capital. It is the majority of engineering economy studies involve a commitment of capital for extended periods of time. So the effect of time must be considered. So the majority of our studies here will be involving capital, and we will be studying how time affects the capital. Then the second is the interest. So what is interest? It is the money paid regularly at a particular rate for the use of money lent or for delaying the payment of a debt. So interest, it is the profit of lenders. So it is acquired through delayed payment. Next is the time value. So it is the characteristic of money. Because of interest or profit, it can earn through time. Yes, the time has also a value, and it also has the effect on money. Next is opportunity cost. Interest or profit available from an alternative investment by using capital in the proposed undertaking. So that is the cost or gain that can be considered from a proposed alternative. So next, the reasons to consider for return of capital. So why do we consider returns for our capital? So there are fundamental reasons why return to capital in the form of interest and profit is essential ingredient of engineering economy studies. First is because it has incentive. So what is incentive? It has interest and profit pay the providers of capital for foregoing its use during the time the capital is being used. So incentive is the reward of the lenders or the investors while their capital is being used. Next is risk. It is the interest and profit are payments for the risk the investor takes in permitting another person or organization to use his or her capital. So because of risk, an investor has the privilege of getting an interest or profit. Okay? So next, here are the origins of interest. So where did interest come from? Okay, so it originated in these terms. So like taxes, interest has existed from earliest recorded human history. So first is the Babylon, 2000 BC. So interest was paid in money for the use of grain or other commodities that were borrowed. It was also paid in the form of grain or other goods. So back then, interest was not only paid by money, it was also paid by other valuable materials. So in other words, interest was paid during this time through barter. Okay, the barter system. Next is the 575 BC. So the idea of interest became so well established that a firm of international bankers existed with home offices in Babylon. The firm's income was derived from the high interest rates it charged for the use of its money for financing international trade. So during these times, there are firms that are uh, bankers, okay? International bankers in Babylon. And such firm was the first ones to impose interest for the use of their money for financial international trade. Next is Exodus 22 verse 21 to 27. So, throughout early recorded history, typical annual rates of interest of loans of money were in the neighborhood of 6% to 25%. Although legally sanctioned rates as high as 40% were permitted in some instances. So these are the interests that were imposed during these times. The charging of exorbitant interest rates on loans was termed usury, and prohibition of usury is found in the Bible. What do you mean by exorbitant? So it is the price charged unreasonably. Okay, so it is unfair to the one who borrows money. Next, the Middle Ages. So interest taking on loans of money was generally outlawed on scriptural grounds. So what does it mean? Outlawed means that it was prohibited during the Middle Ages, the interest taking on loans. Okay? The next is the 1536. The Protestant theory of usury was established by John Calvin, and it refuted the notion that interest was unlawful. So why is that? Because when you say usury, it is about the unlawful lending of money. Okay? So that was a study of John Calvin. So consequently, interest taking again became viewed as an essential and legal part of doing business nowadays. Okay? Eventually, published interest tables became available to the public. Because today, you are freely to lend money to the banks or other lending entities, as long as you have the capacity to pay your debt. Okay? So, next is simple interest. So, when the total interest earned or charged is linearly proportional to the initial amount of the loan principal, the interest rate, and the number of interest periods for which the principal is committed, the interest and the interest rate are said to be simple. So, the keyword here is linearly proportional. So, when such relationship have a linear proportionality, it is a simple interest. So, simple interest is not used frequently in modern commercial practice. So, later you will know why. So, when simple interest is applicable, the total interest, represented by I, big letter I, earned or paid may be computed using this formula. So, I is equal to P, where P is the principal amount lent or borrowed, multiplied by N, where N is the number of interest periods, and multiplied by I, which is the interest rate per interest period. Okay? So as you notice the formula, they have a linear proportionality. Okay? The total amount of repaid at the end of N interest periods is P plus the interest or I. Okay? So thus, if 1,000 pesos were loaned for 3 years at a simple interest rate of 10% per year, the interest valued would be, so you will just substitute the 1,000 here, which is the principal amount, multiplied by 3 because it is in the interest period of 3 years, multiplied by the interest rate, which is 10%. You will convert to decimal, then it is equal to 300 pesos. Okay, so the total amount owed at the end of 3 years would be the principal, which is 1,000 pesos, plus the interest, which is 300 pesos. So it is equal to 1,300 pesos. So notice that the cumulative amount of interest owed is a linear function of time until the principal and interest is paid, usually not until the end of period N. So the principal and the interest will be paid at the end of the period N. So next is the compound interest. So whenever the interest charged for any interest period, example a year, is based on the remaining principal amount plus any accumulated interest charges at the beginning of the period, the interest is said to be compound. So the keyword here is accumulation or accumulated interest for it to be a compound interest. So the effect of compounding of interest can be seen in the following table for 1,000 pesos loaned for 3 periods of an interest rate of 10% compounded each period. So here you notice that there are 3 periods, first, second, and third. So here are the amount owed at the beginning of the period. So you will start with 1,000 pesos. Then this is the interest or the amount for the period. You will just multiply it by the interest rate. So you will get the interest for that period. Okay, so 1,000 multiplied by 10% is 100. Okay, then in the third column, it is the amount owed at the end of the period. You will just add the amount owed at the beginning and the amount and the interest. Okay, for you to have the amount owed at the end of the period. Okay, but here in compound interest, since this involves accumulation, you will use this amount owed at the end period for the second period, okay, up to the last period. So a graphical comparison of simple interest and compound interest is given in this figure. So the difference is due to the effect of compounding, which is essentially in the calculation of interest on previously earned interest. So this difference would be much greater for large amounts of money, higher interest rates, or greater numbers of interest periods. Thus, simple interest does consider the time value of money but does not involve compounding of interest. So compound interest is much more common in practice than simple interest because of the simple reason. Compound interest yields more money or profit. So this figure 5-1 is the illustration of simple versus compound interest. So this one, the graph in the bottom is the simple interest, and the graph in the upper part is the compound interest, which is higher. Okay. Next is the concept of equivalence. So alternatives should be compared when they produce similar results, or they will serve the same. This is not always possible in some types of economy studies, so we will discuss it later. Why it is not possible? So but now our attention is directed at answering the question, how can alternatives for providing the same service or accomplishing the same function be compared when interest is involved over periods of time? Thus, we should consider the comparison of alternative options or proposals by reducing them to an equivalent basis that is dependent on, first is the interest rate, second the amounts of money involved, and lastly is the timing of the monetary receipts or expenses. So for the example 6-1, suppose you have 17,000 pesos balance in your credit card. This has got to stop, you say to yourself. So you decide to repay the 17,000 pesos debt in 4 months. An unpaid credit card balance at the beginning of a month will be charged interest at the rate of 1% by your credit card company. For this situation, we have selected 3 plans. Okay, so we have 3 plans here to repay the 17,000 pesos principal plus interest owed. These 3 plans are illustrated in table 6-1, and we will demonstrate that they are equivalent. Okay, so when the interest rate is 1% per month on the unpaid balance principal. So in this table, you will see that in Plan 1, none of the principal payment is paid, okay, until the 4th month. So the monthly payment is 170 and the principal is repaid at the end of the 4th month. Here in Plan 1, because the interest is not accumulating, compound interest is not present here. So in Plan 1, there are 68,000 peso months of borrowing. So you will just multiply the 17,000 by 4 months. And 680 total interest. You will just sum up all the interest for 4 months. Therefore, the monthly interest rate here is 680 divided by 68,000 peso months times 100% is equal to 1%. Okay? So next, in the Plan 2. So pay off the debt in 4 equal end of the month installments, the principal and the interest. So here, Plan 2, it stipulates that we pay 4,357.1 per month. So later, we will show how we get this value. Okay? For the purposes here, you should observe that the interest is being compounded. Okay? So you will notice that the interest is being compounded, that the 17,000 pesos principal is completely repaid over the 4 months. Because in this principal column, you notice that the 17,000 is repaid in 4 months. From table 6-1, you can see that the monthly interest rate is 427.10 divided by 42,709.5 peso months borrowing times 100 is equal to 1%. So it is the same with the plan 1. Okay? So there are fewer peso months of borrowing in Plan 2 as compared with Plan 1. Why? Because principal is being repaid every month and the total amount of interest paid is 427.10 peso is less. So that implies that when you pay the principal every month, the interest will be lesser. Okay? Then finally, in Plan 3 shows that no interest and no principal are paid in the first 3 months. Then at the end of the month 4, a single lump sum amount of 17,690.27 pesos is repaid. So this includes the original principal and the accumulated compounded interest of 690.27. So there is a compound interest here in Plan 3. So the peso months of borrowing are very large for Plan 3. Because it is equals to 69,026.8 because none of the principal and accumulated interest is repaid until the end of the 4 months. So that it will entail, okay, if you do not pay the principal and the interest per month, the peso months of borrowing will be large. So again, the ratio of total interest paid to peso months is 1%. Okay. So when you do this computation again to get the percentage, thus we have shown that they are the same. Okay, so this brings us back to the concept of economic equivalence. So if the interest rate remains at 1% per month, you should be indifferent as to which plan you use to repay the 17,000 pesos to your credit card company. So this assumes that you are charged 1% of the outstanding principal balance, which includes any unpaid interest each month for the next 4 months. If interest rates in the economy go up and increase your credit card rate to say 1 1/4% per month, the plans are no longer equivalent. So what varies among the 3 plans is the rate at which principal is repaid and how interest is repaid. Next, for the notation and cash flow diagrams and tables, the following notation is utilized in formulas for compound interest calculations. Letter I is equal to the effective interest rate per interest period. N is equal to the number of compounding interest periods. So P is equal to present sum of money, the equivalent value of one or more cash flows at a reference point in time called the present. So F is the future sum of money, the equivalent value of one or more cash flows at a reference point in time called the future. And A is the end of the period cash flows or equivalent end of period values in a uniform series continuing for a specified number of periods, starting at the end of the first period and continuing through the last period. So those are the notations that you should remember, and we will be using that in solving problems here. So the use of cash flow time diagrams or tables is strongly recommended for situations in which the analyst need to clarify or visualize what is involved when flows of money occur in various times. In addition, viewpoint principle 3 of the engineering economy is an essential feature of cash flow diagrams. So the difference between the total cash flows or the receipts and the cash outflows or the expenditures for a specified period of time, example 1 year, is the net cash flow for the period as discussed in Module 1. Cash flows are important in engineering economy because they form the basis for evaluating alternatives. Indeed, the usefulness of cash flow diagram for economic analysis problem is analogous to the free body diagram for mechanics problem. So, this cash flow diagram is just like the one that you are using in the mechanics. Okay? They are equivalent in terms of their importance in studying. So this figure 7-1 shows a cash flow diagram for Plan 3 of Table 6-1, and figure 7-2 depicts that net cash flows of Plan 2. Okay? The next figure. So this is it, the figure 7.2 cash flow diagram for Plan 2 of Table 6-1 lender's point. So these two figures also illustrate the definition of the preceding symbols and their placement on a cash flow diagram. So notice that all cash flows have been placed at the end of the month to correspond with the convention used in Table 6-1. In addition, a viewpoint has been specified. So you notice in the cash flow, you have your P or the principal amount, 17,000 pesos. So this is the beginning of the month 1. So this is the viewpoint. Then end of the month. Okay? First end of the month, end of the second month, third month, and the fourth month. So we have a cash flow with the end of the month. Then the interest rate is equal to 1% per month. And this will be the future value. Okay? That will be paid at the end of the fourth month, which is 17,690.27 pesos. So this is based in the Plan 3. So this is how you do a cash flow diagram. So next is so here you notice that in figure 7-2, the cash flow diagram for Plan 2 have the annuities or capital letter A for end of the month. Okay? So that is the difference of the two cash flows for Plan 3 and Plan 2. So next, the cash flow diagram conventions. For the horizontal line is the time scale, the progression of time moving from left to right. Okay, so the period, example year, quarter, or month, labels can be applied to intervals of time rather than to points on the time scale. So you can have these intervals depending on the problem. So note, for example, that the end of period 2 is coincident with the beginning of period 3. When the end of the month cash flow convention is used, period numbers are placed at the end of each time interval. Okay, so as illustrated in the figures above. So here are the periods number. The month 1, 2, 3, 4. The same with this 1, 2, 3, 4 months. Okay. Next are the arrows. So significant cash flows and are placed at the end of the period. If a distinct needs to be made, downwards arrows represent expenses or negative cash flows or cash outflows, and upward arrows represent receipts, positive cash flows or cash inflows. So here you notice the downwards arrow means outflows and the upward means positive cash flows or inflows. Next, the point of view, where cash flow diagram is dependent. For example, the situation shown in figures 7-1 and 7-2 were based on cash flows as seen by the lender, so the credit card company. If the directions of all arrows had been reversed, the problem would have been diagrammed from the borrower's viewpoint. So if we reverse the arrows here, okay, then it will be representing the borrower's viewpoint. So example 7-1, cash flow diagramming. So before evaluating the economic merits of a proposed investment, XYZ Corporation insists that its engineers develop a cash flow diagram of the proposal. So an investment of 10,000 pesos can be made that will produce uniform annual revenue of 5,310 pesos for 5 years, and then have a market recovery value of 2,000 pesos at the end of the year, or abbreviated as EOI. Okay, 5. So annual expenses will be 3,000 pesos at the end of each year for operating and maintaining the project. So draw a cash flow diagram for the 5-year life of the project. So use the corporation's viewpoint. So for the solution, as shown in the figure below, the initial investment of 10,000 pesos is here. Okay, so it is represented by a downward arrow because it is an expense of the company. And annual expense of 3,000 pesos are cash outflows. Okay, so every end of the month, you have 3,000 pesos represented by the downward arrows because they are outflows of the company. So while annual revenues and the market value are cash inflows. So here are the market values represented by upward arrows because they are income or profit to the company. Okay. So notice that the beginning of the given year is the end of the preceding year. Okay. For example, the beginning of the year 2 is the end of year 1. Okay, this is the year 2, this is year 1. So the beginning will be the end of the other. So next example, 7-2, developing a net cash flow table. So in a company's renovation of a small office building, 2 feasible alternatives for upgrading the heating, ventilation, and air conditioning or HVAC system have been identified. So either alternative A or alternative B must be implemented. So the costs are as follows. For alternative A, which is about rebuilding or overhaul of the existing HVAC system, the equipment, labor, and materials to build cost 18,000 pesos, and the annual cost of electricity is 32,000 pesos. Annual maintenance expense is 2,400. So for the alternative B, to install a new HVAC system that utilizes existing ductwork, equipment, labor, and materials to install is 60,000 pesos. Annual cost of electricity is 9,000, and annual maintenance expense is 16,000. Replacement of major component for 4 years hence is 9,400. So those are the given. So at the end of 8 years, the estimated market value for alternative A is 2,000 pesos, and for alternative B, it is 8,000 pesos. Assume that both alternatives will provide comparable service motor over an 8-year period, and assume that the major component replaced in alternative B will have no market value at EOY 8. So use a cash flow table at the end year convention to tabulate the net cash flows for both alternatives. Next, you will determine the annual net cash flow difference between the alternatives B and A. So for the solution, the cash flow table company's viewpoint for this example was developed by using a spreadsheet and is shown in the next figure 7-3 on the basis of these results. Number 1, doing nothing is not an option. Either A or B must be selected. So the company should select one of the two, alternative A or alternative B. Number 2, even though positive and negative cash flows are included in the table, on balance, we are investigating two cost-only alternatives. So here in the figure, even though they are negative because they are enclosed in the parentheses, okay, we are just investigating the cost of these alternatives. Number 3, a decision between the two alternatives can be made just as easily on the difference in cash flows. An example on the avoidable difference, as it can on the standalone net cash flows for alternatives A and B. So here, the two alternatives are easily compared by their difference. Okay. Alternative B has cash flows identical to those of alternative A, except for the differences shown in the table. So if the avoidable difference can pay its own way, alternative B is the recommended choice. So alternative B is the same with alternative A because they are all negatives here. Okay, but as you notice that the amounts of the under alternative B are lower than the alternative A. So if the avoidable causes here of the amount can be compensated, then alternative B will be selected. Number 5, cash flow changes caused by inflation or other suspected influences could have easily been inserted into the table and included in the analysis. So you can simply insert this inflation factors by inserting cells there. Okay. Number 6, it takes 6 years of the extra 42,000 pesos investment in alternative B to generate sufficient cumulative savings in annual expenses to justify the higher investment. So here you notice that an extra 42,000 investment in alternative B, because the difference of this 18,000 and 60 is 42. Okay. So it will take 6 years because in the end of the 6 years, you will have a positive value here in the cumulative difference. So it will take 6 years. So this ignores the time value of money. So which alternative is better? We'll be able to answer this question later when we consider the time value of money in order to recommend choices between alternatives. So we will be discussing first the time value of money. So next, relating present and future equivalent values of single cash flows. So figure 8-1 shows a cash flow diagram involving a present single sum P and the future single sum F, separated by n periods with the interest at 1% per period. Throughout this module, a dash arrow, such as shown in figure 8-1, indicates the quantity to be determined. So this is the figure 8-1. This is the present equivalent value. This will be given, and this is the interest rate per period. Okay, per period 1, 2, 3, 4, 1, 2, 3 up to n period. This is the future equivalent. So this is the one you will find, the letter F. So this is the general cash flow diagram relating to the present equivalent and future equivalent of single payments. So finding F when given is P in an amount of P pesos is invested at a point in time, and I% is the interest, profit or growth per rate per period. The amount will grow to future amount of P plus P times I is equal to P multiplied by the quantity 1 plus I by the end of one period. So by the end of 2 periods, the amount will grow to P multiplied by quantity 1 plus I multiplied by quantity 1 plus I is equal to P multiplied by the squared of the quantity 1 plus I. Okay, so by the end of 3 periods, the amount will grow to this. You notice that we are just adding exponents here. Okay, so and by the end of the n periods, the amount will grow to this general formula, our equation 8-1. F is equal to P multiplied by the quantity 1 plus I raised to n. Okay, so for the example problem, the future equivalent of a present sum. Suppose that you borrow 8,000 pesos now, promising to repay the loan principal plus accumulated interest in 4 years at I is equal to 10% per year. How much would you repay at the end of the 4 years? So for the solution, you can refer to this table. So these are the years, year 1 to 4, and these are the amount owed at start of the year. So in the first year, you have 8,000 pesos. Okay? So for the interest on for each year, you will just get the 10% of the amount owed at start of the year, which is 800. Then amount owed at the end of the year, you will just add these two. 8,000 plus 800 is equal to 8,800. In the total end of the payment, you will not pay at the end of the first period, of course, because the problem is about paying at the end of the 4th year. Okay? So this amount owed at the end of the year will be used here as a starting amount owed at the start of the year of the 2nd year. Okay? Then you will use this formula for it to get the interest owed for it. Then you will add again. Okay? Then you will just do it for the rest until you reach the year 4. Okay? And then in the year 4, you will pay this amount owed at the end of the year. Okay? So it is 11,713. So the quantity 1 plus I raised to n in equation 8-1 is commonly called the single payment compound amount factor. So numerical values for this factor are given in the second column from left in tables of the appendix for a wide range of values of I and n. So this is the appendix. So you will find that in this second column, okay, to find f given p or f given p, so you will find these values. Okay, so in this module we shall use this functional symbol f dash p, quantity f dash p, comma I percent, comma n for the quantity 1 plus I raised to n. So hence for the equation 8-2 can be expressed by this. Okay, so this is our equation 8-2, where the factor in parentheses is read as find f. Okay, find f given p. Okay, at I percent interest per period for n periods. Okay, so you will read that by this. Okay, so find f given p at I interest per period for n interest periods. Note that the sequence of f and p and f dash p is the same as in the initial part of equation of 8-2. Okay, because you have f here and you have p here. Okay, so where the unknown quantity f is placed on the left hand side of the equation. This sequence of letters is true of all functional symbols used in this module and makes them easy to remember. So let's look again at example 8-1 using 8-2 and appendix we have. So using this formula, okay, we will find this in the appendix. Okay, you can also use the appendix or you can use this formula. So to find this, we will go to the appendix. Okay, so find this discrete compounding I, the interest is equal to 10%, and you will select n is equal to 4. So under the column of find f given p. Okay, so you have 1.4641. That's why you have 1.4641 here. Okay, so multiply it, you have 11,713 pesos. Next, another example of finding f when given p together with a cash flow diagram and solution appears in table 8-1. So here is another example of it. A firm borrows 1,000 pesos for 8 years. How much must it repay in a lump sum at the end of the 8th year? So in equivalence terminology, what is the future equivalent at the end of 8 years of 1,000 pesos at the beginning of those 8 years. So in this cash flow diagram, you notice that P is equal to 1,000 pesos and is represented by upward arrow because there is an inflow of money to the firm. Okay, then you have your end periods, which is 8, and the value of F, which is the one to find out, and it is represented by downward dash arrow. Okay, because this will be an outflow. Then using the formula, okay, F is equal to P when finding F and given is P at 10% interest and 8 years periods. Okay, so you got 2,143.6 pesos. Okay, so note in the table 8-1 that for each of the 6 common discrete compound interest circumstances covered, 2 problem statements are given. The first one is about borrowing to lending terminology. The second one is the equivalence terminology, but they both represent the same cash flow situation. Indeed, there are generally many ways in which a given cash flow situation can be expressed. In general, a good way to interpret a relationship such as equation 8-2 is that the calculated amount F at the point in time at which it occurs is equivalent to, example, can be traded for to the known value of P at the point in time at which it occurs for the given interest profit, which is represented by profit rate, which is represented by I. Next, finding P when given F. So from the equation 8-1, so it is the equation 8-1, solving this P gives the relationship this, okay? So P is equal to this, F multiplied by the quantity 1 plus I raised to negative n. So it is our equation 8-3. So the quantity 1 plus I raised to negative n is called the single payment present factor. Okay, so the numerical values for this factor are given in the third column of the table in appendix for a wide range of values I and n. So we can see that here in the third column to find P given F. Okay, we shall use the functional symbol P-F I%n for this factor. Hence, P is equal to F multiplied by the quantity P-F I%n. So that is our equation 8.4. For example, 8-2, present equivalent of a future amount of money. An investor or the owner has an option to purchase a tract of land that will be worth 10,000 pesos in 6 years. If the value of the land increases at 8% each year, how much should the investor be willing to pay for this property? So for the solution, the purchase price can be determined from equation 8-4 in table C sub 11 in appendix. So P is equal to the future value, which is 10,000. Okay, multiply by this, we will find this in the appendix. So 8% and 6n. So we will go to 8%. So in the appendix, this is 8% and we have 6n. So we will use 0.6302. That's why it is 0.6302 here. So when we multiply it, we have 6,302 pesos. So another example of this type of problem together with the cash flow diagram and solution is given in table 8-1. So here it is. You will have to find P given F. So a firm wishes to have 2,143.6 pesos 8 years from now. Okay? What amount should be deposited now to provide for it? So next, what is the present equivalent of 2,143.6 pesos received 8 years from now? So to draw its cash flow diagram, you notice that the given is the future value. Okay, that's why it is represented here, okay, in the last part, and it is represented by the upper arrow, or an arrow pointing to upwards, okay? Because it is an inflow to the company, while the present value is represented by downward arrow and dash line because it is the one we are going to find, and it is an outflow to the company. So using the formula, setting 10% interest in 8 years, and the future value of 2,143.6, you have 1,000 pesos. Okay? Next, based on equations 8-1 and 8-3, the following three simple rules apply when performing arithmetic calculations with cash flows. So, Rule A, cash flows cannot be added or subtracted unless they occur at the same point in time. Okay? Next, Rule B, to move a cash flow forward in the time 1 by 1, one-time unit, okay, multiply the magnitude of the cash flow by 1 plus I, where I is the interest rate that reflects the time value of money. Then Rule C, to move a cash flow backward in time by one time unit, divide the magnitude of the cash flow by quantity 1 plus I. So those are the three rules with the equations 8-1 and 8-3. Next, finding the interest rate given P, F, and N. So there are situations in which we know two sums of money, the present and the future, okay, and how much time separates them, okay, but we don't know the interest rate or I. That makes them equivalent. For example, if you want to turn 500 pesos into 1,000 over a period of 10 years, at what interest rate would we have to invest it? We can easily solve the equation 8-1 to obtain an expression for I. So we have our equation 8-5 to get I. I is equal to the nth root of f dash p minus 1. So for our simple example, I is equal to the 10th root of 1000 divided by 500 minus 1 is equal to 0.0718 or 7.18% per year. So inflation is another example of when it may be necessary to solve for an interest rate. Suppose you are interested in determining the annual rate of increase in the price of gasoline. Given the average prices in the different years, you can use the relationship between P and F to solve the inflation rate. So, example 8-3, the inflating price of gasoline. So, the average price of gasoline in 2005 was 111.18 pesos per gallon. In 1993, the average price was 51.5 pesos. What was the average annual rate of increase in the price of gasoline over this 12-year period? So for the solution with respect to the year 1993, the year 2005 is in the future. Thus, P is equal to 51.5 pesos and F is equal to 111.18 pesos. And N is equal to 12 years because 1993 to 2005 is an interval of 12 years. So using equation 8-5, we find this. I is equal to the 12th root of 111.18 divided by 51.5 minus 1 is equal to 6.62% per year. Next, 8.3, finding N when given P, F, and I. Sometimes we are interested in finding the amount of time needed for a present sum to grow into a future sum at a specified interest rate. For example, how long would it take for 500 pesos invested today at 15% interest per year to be worth 1,000 pesos? We can use the equivalence relationship given in equation 8-1 to obtain an expression for N. So this one is equation 8-1. So you will just transpose and you will use logarithms. Okay? Then it will be like this, and logarithm of the quantity 1 plus I is equal to logarithm of F over P or F dash P. And thus N is equal to logarithm of f dash p over logarithm of 1 plus I. Okay, for our example, okay, so n is equal to the logarithm of 1000 divided by 500 over logarithm of 1 plus 0.15 because we have 15% here. So it is equal to 4.96 or approximately 5 years. Okay? So now relating a uniform series annuity to its present and future equivalent values. So figure 9-1 shows a general cash flow diagram involving a series of uniform equal receipts, each of amount A occurring at the end of each period for n periods with interest at I% per period. Such a uniform series is often called as annuity. It should be noted that the formulas and tables to be presented are derived such as A occurs at the end of each period. Okay? And thus P, the present equivalent value, occurs one interest period before the first A uniform amount. And F, future equivalent value, occurs at the same time as the last A. And N periods after P. And last, number 3, A annual equivalent value occurs at the end of periods 1 through N, exclusive. The timing relationship for P, A, and F can be observed in this figure. So for formulas relating A to F and P will be developed here. Okay, you notice that this is the present equivalent value. Okay, so this is the one that can be asked in the problem. So these are the annuities, meaning they are equals for each end of the periods, for each periods. Okay, and this is the n number of interest periods. And last, this is the F or the future equivalent. So this is the general cash flow diagram relating uniform series or ordinary annuity to its present equivalent and future equivalent values. Now finding F given A, if a cash flow in amount of A pesos occurs at the end of each period for n periods and I% is in the interest, profit or growth rate per period, the future equivalent value F at the end of the n period is obtained by summing the future equivalents of each of the cash flows. Thus, the F is equal to A quantity FP I% n minus 1, then up to this. Okay? So the bracketed terms comprise a geometric sequence having a common ratio of the quantity 1 plus I raised to 1. So recall that the sum of the first n terms of a geometric sequence is this. Okay? Where B is not equal to 1. So, where A is the first term of the sequence, okay, this A sub 1 is the first term, A sub n is the last term, and B is the common ratio. So, if we let B is equal to this, quantity 1 plus I raised to negative 1, and A sub 1 is equal to quantity 1 plus I raised to negative n minus 1, and A sub n is equal to 1 plus I raised to 0, then we have this formula. So that is the derivation of the formula, of this formula. So the equation 9-1, so F is equal to A multiplied by the quantity 1 plus I raised to n minus 1 over I. Okay, so that will be our formula. So the quantity 1 plus I raised to n minus 1 divided by I all over I is called the uniform series compound amount factor. Okay, it is the starting point for developing the remaining 3 uniform series interest factors. So numerical factors for the uniform series compound amount factor are given in the 4th column of the tables in appendix for a wide range of values of I and N. So it is here in the 4th column to find F given A. Okay? We shall use the functional symbol F-A I% N for this factor. Hence, the equation 9-2 is this. F is equal to A multiplied by the quantity of the functional symbol. So for an example, for 9-1, the future value of a college degree. So a recent government study reported that a college degree is worth an extra 23,000 pesos per year in income, compared to what a high school graduate makes. If the interest rate I is 6% per year and you work for 40 years, N, what is the future compound amount F of this extra income? So for the solution, the viewpoint we will use to solve this problem is the lending, the 23,000 pesos of extra annual income to say a savings account or some other investment vehicle. The future equivalent is the amount that can be withdrawn after the 40th deposit is made. Okay? So in a cash flow, it is like this. So graduate from college. Okay? From 0 year, 1 to 3, up to 48 year. So here is the annuities. Okay? Meaning the equal outflows. Okay? 23,000 pesos each year. So this is from the lenders, okay? Lender's point of view. That's why this annuities are towards down, okay? Downwards, okay? Because the money is going outside the lender, okay? That's why it is pointing downwards. So here are the investments, annuities per period. So notice the future equivalent occurs at the same time as the last deposit of 23,000 pesos. Okay, because we have a downward arrow here in the last deposit. So using the formula, we have this. F is equal to 23,000 pesos, and we will look this in the appendix. So we'll go here to I is equal to 6%. Then we will look for the 40N. Okay, 40N under this to find F given A. Okay, so the 40 here is this. So its equivalent is this, 154.7620. That's why it is 154.7620 here. Then you will multiply it with 20,000 pesos. It is equal to 3,559,526 pesos. Okay? Next, finding P when given A. So from equation 8-1 again, substituting F in the equation 9-1, we determine that to find P given A, we have this equation. Okay? P is equal to A multiplied by the quantity 1 plus I raised to n minus 1 all over I multiplied by the quantity 1 plus I raised to n. Okay, so that is our equation 9-3. Thus, the equation 9-3 is the relation for finding the present value, equivalent value as of the beginning of the first period of a uniform series of end-of-period cash flows of amount A for n periods. The quantity in brackets, so this is the quantity in brackets, is called the uniform series present worth factor. Okay, so the numerical values for this factor are given in the fifth column of the tables in appendix. So here it is, the fifth column. So 1, 2, 3, 4, and 5 to find P given A. Okay, and of course we also have here our functional symbol P-A, I%, and N. So this is our equation 9-4. Okay, so for the example 9-2, present equivalent of an annuity, uniform series. A microbrewery is considering the installation of a new design boiler system that burns the dried, spent malt, and barley grains from the brewing process. The boiler will produce process steam that powers the majority of the brewery energy operation, saving 450,000 pesos per year over the boiler's expected life of 10 years. If the interest rate is 12% per year, how much money can the brewery afford to invest in the new boiler system? So for the solution, in the cash flow diagram below, notice that the affordable amount, example the present equivalent P, occurs one-time period before the first end of year cash flow of 450,000 pesos. So here it is. Okay, the present amount occurs before the first period. So the increase in annual cash flow is 450,000 pesos. It is the annuities. Okay, so it is represented by upward arrows because it is an inflow to the company because it is a savings. Okay, the boiler saves. Okay, and it continues for 10 years at 12% annual interest. So the upper limit on what the brewery can afford to spend on the new boiler is this. Using the formula, P is equal to the annuity, which is 450,000 pesos, and this our formula. So we will look for this in the appendix, or we will use the given equations above. So to find this, we will go to the appendix, which is 12%, and the given n, which is 10. So it is here in the fifth column. It is equal to 5.6502. That's why it is 5.6502 here. So it is equal to 2,542,590 pesos. Okay, so example 9-3. How much is a lifetime oil change offer worth? So if you purchase a car from a dealership, you expect to have 4 free oil changes per year during the 5 years you keep in the car. Each oil change would normally cost you 1,500 pesos. If you save your money in a mutual fund earning 2% per quarter, how much are the oil changes worth to you at the time you buy the car? So for the solution, in this example, we need to find the present equivalent of the cost of future oil changes. The cash flow diagram is shown below. Notice that P occurs one time period, a quarter of a year, in this example, before the first oil change cash flow, A. So this is it, the present value. It occurs before first period. Okay? So one period is equal to a quarter. Okay? So the interest rate is 2% per quarter. And the total for oil changes per year times 5 years is equal to 20 oil changes cash flows are anticipated. That's why in the formula you have 1,500 pesos and you will use this quantity. Okay? When you look at this in the appendix, it is equal to 16.3514. So the answer is 24,527.1 pesos. So now you are in position to determine how great a deal you are being offered. If the price of another dealership is more than the answer, cheaper than what you are being offered at this dealership, maybe this deal isn't so great. Okay? So finding A when given F. So taking the equation 9-1 and solving for A, we find the equation 9-5. So A is equal to F multiplied by the quantity I over 1 plus I raised to n minus 1. So thus, equation 9-5 is the relation for finding the amount A of a uniform series of cash flow occurring at the end of n interest periods. That would be equivalent to have the same value as its future value occurring at the end of the last period. So the quantity in the brackets, this quantity in the bracket is called the sinking fund factor. Numerical values for this factor are given in the 6th column of the tables in the appendix. So it is here. So 1, 2, 3, 4, 5, 6 to find A given F. Okay? So, and we will use this functional symbol. Okay? So A, that is our equation 9-6. A is equal to F multiplied by the functional symbol. So another example of this type of problem together with the cash flow diagram and solution is given in the table 8-1. So here it is. To find A given F. So what uniform annual amount should be deposited each year in order to accumulate 2,143.6 at the time of the pesos at the time of 8 annual deposit. So what uniform payment at the end of 8 successive years is equivalent to 2,143.6 pesos at the end of 8 years. So this is the cash flow diagram. So here are the 1 to 8 periods. So what is the annuities? Okay, the annuities for those periods, given the future equivalent of 2,143.6 pesos. So you will just use the formula. A is equal to the given F multiplied by the corresponding value in the appendix, and you will have 187.45 pesos is the annuity for each of these periods. So going back to proceed, find A when given P. So taking equation 9-3 and solve for P, we find that A is equal to P multiplied by the quantity I multiplied by 1 plus I raised to N all over the quantity 1 plus I raised to N minus 1. So it is our equation 9-7. So this equation is the relation for finding the amount of A of a uniform series of cash flows occurring at the end of each of N interest periods that would be equivalent to or could be traded for the present equivalent P occurring at the beginning of the first period. The quantity in the bracket, so this is the quantity in the bracket, is called the capital recovery factor. Okay, numerical factors or numerical values for this factor are given in the 7th column of the tables in appendix. So this is it in the appendix 1, 2, 3, 4, 5, 6, 7 to find A given P. Okay, and of course we have the formula for that. A is equal to P multiplied by A dash P I percent N. So that is our equation 9-8. Example 9-4, equivalence between a present lump sum loan amount of a series of equal uniform monthly payments starting at the end of month 1 and continuing through the month 4. Okay, so here the figure 9-2 is the relationship of cash flows for plan 2 of table 6.6-1 to repayment of the 17,000 pesos loan principal. So this problem is originated from the plan 2 in the table 6-1. Okay, so here you notice that for each period there are 4 periods here, and they have annuities of 4,357.10. Okay, for each period. So equation from the equation 9-8 yields the equivalent value of A that repays 17,000 loan plus 1% interest per month for over 4 months. So here it is. So A is equal to the present value, which is the 17,000 pesos. And when we look this in the appendix, it is equivalent to 0.2563. You will just multiply them. That's why it is equal to 4,357.10. So now you know where how do we get 4,357.10 annuities. Okay, so the entries in columns 3 and 5 of plan 2 in table 6-1 can now be better understood. Interest owed at the end of the month 1 equals 17,000 multiplied by 1%, and therefore the principal repaid out of the total end of the month payment of 4,357.10 is the difference. Okay, so 4,187.10. So this is it, the difference. You will just subtract them. Okay, so if you subtract, we'll just get 12,812.90 interest owed at the end of the month too. So you get this 4,187.10 by just subtracting. Okay, subtracting the product of this, the 17,000 times 0.01 to this. Okay, so here you will just get this computation for the end of the month too. Okay, we'll just multiply this new principal owed by 1%. That's why you get 128.13. Okay? And the principal repaid at that time is same. Okay? You will just subtract it with this. That's why it becomes 4,228.97. Okay? So the remaining entries in Plan 2 are obtained by performing these calculations for the months 3 and 4. So this is the explanation for that Plan 2. Okay? Next, 9.5, finding the number of cash flows in an annuity given A, P, and I. Sometimes we may have information about the present amount of money, P, the magnitude of the annuity A, and the interest rate I. The unknown factor in this case is the number of cash flows in the annuity N. Okay? So example 9-5, prepaying a loan, finding N. Your company has 100,000 pesos loan for a new security system it just bought. The annual payment is 8,880 and the interest rate is 8,000 per year for 30 years. Your company decides that it can afford to pay 10,000 pesos per year. After how many payments or years will the loan be paid off? So for the solution, the original loan payment was found using the equation 9-8. Okay? Because when you substitute this, the present value, which is 100,000 pesos, with this equation, you will get 8,800 pesos per year. Okay? You will get the annuities. So now, instead of paying 8,880 per year, your company is going to pay 10,000 pesos per year. Common sense tells us that less than 30 payments will be necessary because 10,000 is higher than 8,880. Okay? Using equation 9-4, we find this. So you will just substitute. Okay? The present value is this, and the future value or the annuities is 10,000 pesos. Okay? Then dividing both by 10,000, you will get 10. Okay? We can now use the interest tables provided in the appendix to find N. Looking down the present worth factor column P-A of the table, we see that. So we will find these values. Okay? 9.818, then 10.0168 because it is where 10 lies. Okay? In between of them. So this first value is in 8% and 20. Then the second value belongs to 8% and 21. So if 10,000 pesos is paid per year, the loan will be paid off after 21 years instead of 30. Okay? So we will choose this higher value. Okay? The exact amount of 21st payment will be slightly less than 10,000 pesos. Okay? So it will be slightly less than 10,000 pesos because there are excess here. Okay? It is not equal to 10. 9.6, finding the interest rate I given A, F, and N. So this part is when you know the amount of A, the duration N, and the uniform payment series, as well as the desired future value of series F. So here, the interest rate that makes them equivalent is missing. So, for the example 9-6, finding the interest rate to meet an investment goal. After years of being poor, debt, encumbered college student, you decide that you want to pay for your dream laptop in cash. Not having enough money now to decide, you decide to especially put money away each year in a dream laptop fund. The laptop you want to buy will cost 60,000 pesos in 8 years. You are going to put aside 6,000 each year for 8 years. To save for this, at what interest rate must you invest your money to achieve your goal of having enough to purchase the laptop after 8 years? So for the solution, we can use equation 9-2 to show our desired equivalence relationship. So this 60,000 pesos is the future value, and this is the annuities of 6,000 pesos. Then if we simplify that, we will get 10. So now we can use the interest tables in appendix to help track down the unknown value of I. What we are looking for are two interest rates, one with the F-A I percent 8 value greater than 10, and one with F-A I percent 8 less than 10. So thumbing through the appendix, we will find this, because this is where 10 lies in between of them. Okay, so this one 6% and 8 is equal to 9.8975. This one is 7% and 8 is equal to 10.2598. Okay, so this tells us that the interest rate we are looking for is between 6% and 7% per year. Okay, so even though the function f-a I percent n is nonlinear, we can use linear interpolation to approximate the value of I. Okay, so the dashed curve in the figure 9-3 is what we are linearly approximating. So the answer I can be determined by using the similar triangles dashed in figure 9-3. So this is it, the dash curve. It is what we are approximating here. Okay, so this is using interpolation to approximate I in example 9-6. So using the interpolation, I minus the 6% over 10 minus 9.8975 is equal to 7% minus 6% all over 10.2598 minus 9.875. So that is the interpolation. So if you can find an investment account that will earn at least 6.28% interest per year, because it is the resulting value of our interpolation, you'll have the 60,000 pesos you need to buy your dream laptop in 8 years. Okay? So next is the summary of interest formulas and relationships for discrete compounding. So table 10-1 provides a summary of the 6 most common discrete compound interest factors utilizing notation of the preceding section. So here are the summary. Okay, table 10-1. Okay, to find and given. Okay, and the formula and the factor name. Okay, and also the factor functional symbols. So the formulas are for discrete compounding, which means that the interest is compounded at the end of each finite length period, okay, such a month or a year. Furthermore, the formulas also assume discrete. Example, lump sum cash flows is spaced at the end of the equal time intervals on cash flows diagram. Discrete compound interest factors are given in appendix, where the assumption is made that I remains constant during the n compounds periods. Okay, so these are also several useful relationships between the compound interest factors. So these relationships are summarized in the following equations. Okay, so they are equalities here. Okay, so from equation 10-1 to equation 10-7. So you should note these formulas. So that's all. This is the appendix. Then you will answer the post-test. Okay? So post-test, answer the following in a clean short bond paper. Avoid erasure. Show complete solution. The number in parentheses. So here, the number here indicates the the section from which the problem is taken. So you have your reference. Okay? Reference part of the lecture.